Okay, in this lesson, we're going to learn what a geometric sequence is. This is lesson 1.2 of illustrative math. So lesson 1.2 is called Introducing Geometric Sequences. So our goal today is I understand what a geometric sequence is, and I can find missing terms in a geometric sequence. Obviously, the word that you're probably looking at right there is the word geometric sequence right there. Okay, we're going to learn what that is. You don't know that word yet, but we learned what a sequence was in lesson 1.1. So we're going to learn what a geometric sequence is today. All right, what do you notice? What do you wonder? Okay, pause the video, take a look, try to come up with some things. All right, you might notice that these two are increasing and these two are decreasing. All right, getting smaller, and the first two are getting bigger and the second two are getting smaller. You might be able to notice that you're multiplying on, I think, all of them actually, times 3. Okay, on the first one. Second one would be times 4. Okay. Now it's very tempting on the next two to say divided by. Like, honestly, most kids look at this and they say, "Oh, I'm dividing by 2." Okay, but um, in a geometric sequence, you're always going to be multiplying by a value. So instead of saying divided by 2, we're going to say we're multiplying by 1/2. Okay, so these are all going to be times 1/2. Okay, times 1/2. And that's the same as dividing by 2. Now, if it was dividing by 3, you would times it by 1/3. Okay, dividing by 4, times it by 1/4. Okay, you're always going to be multiplying. Now, this one's even trickier. So here's a little trick. If you can't tell what you're multiplying by, you could always divide the numbers. So we're always going to divide by the previous number. So if I took 192 and divided by 256, I'm going to get 0.75 or 3/4, either one. All right. Since 0.75 is an exact decimal, I'll just leave it. If I had to round it, I'd probably put it as a fraction because I don't like rounded decimals in math. Okay. But there you go, times 0.75. Okay. So there's some notices, there's some wonders. And just, to foreshadow what we're going to do today, all 4 of these are geometric sequences. Okay. Geometric sequences are basically sequences that you multiply to get the next term. So as I look here, what's the common ratio? Is the common ratio is the number that you multiply by. Common ratio is the number multiplying by. So in each one of these, we have a common ratio. So the first one is, let's see, the first one is 3. The second one's 4. The third one is 1/2, and the last one is 0.75. Okay, so that's the number you multiply by. Okay, and then the other value is your initial value or your initial term. Okay, so if I look here, my initial term, I'll use a highlighter here. So my initial term here is 42, 1,256. And my common ratio, I'll use yellow here, would be what you multiply by each time. Okay. And a lot of times we actually call the initial term, or the common ratio, we call it R, and the initial term, we call it A1 or F1 or whatever you want to use to call your function. Okay, but it's the first term, A1 usually. Okay, so let's take a look at a situation here. Claire takes a piece of paper, cuts it in half, then stacks the pieces. Then she takes the stack of 2 pieces, then cuts them in half again to form 4 pieces, stacking them. She keeps repeating the process, okay? So what you end up having here is, let's just draw a sheet of paper here. And if I cut it right here. I know it's not perfectly half. So we start out with 0 cuts. We obviously have 1 sheet of paper. And the original paper has a length of 8 by 10. So area in square inches of each piece. So it'd be 8. Let's get whoops. Let me tell you what, let me get rid of that cut. Let's start with the first piece first. So it's 8 by 10. So the area of that piece is obviously 8 times 10, 80. 80 square inches. Okay, so then we're going to cut it. We're going to cut it right. You know what? I want a dotted line. So we cut it right there. Okay. So now we have 2 pieces, obviously. So I'm going to write that in. And then if this was 10, the top one's going to stay the same at 8, and this is going to be 5. Okay, so I'm going to just look at one piece right here. I'll look at the top one. So the area of that is 40. Okay. And then I'm going to cut that piece in half again. Okay. So you're really going to cut them all in half. Okay. But I'm just going to focus on the top one here. So if I cut that in half, it'll look something like that, roughly. Okay. So now I'll just look at the top piece again. What's this length? Well, it went from 5 to 2.5. So the area of that is going to be 8 times 2.5. So that's 20. And we really have 4 pieces now because we really cut all of them because we stacked them on top of each other. So down here, this would get cut again. So you can kind of now see the pattern here. So it looks like the number of pieces is being multiplied by 2. So I think I could kind of go ahead and finish out my table here. And then the area is getting cut in half. So this is going to go 10, 5, 2.5. So this whole column here is times 1/2. And this whole column is times 2 all the way through. Okay. So back to what we were talking about on the warm up, the common ratio for the first column, number of pieces, is 2. And the common ratio for the second column is 1/2. Okay. So maybe if I write it down here, R equals 1/2. R equals 2 there. Okay, so we have basically 2 different types of geometric sequences right there. Okay, one that's getting bigger and one that's getting smaller. Or to do a little foreshadowing here, we have one that is growing and one that's getting smaller and smaller. So we'll say that it's decaying. Okay. All right. So describe how you can use the results after 5 cuts to find the results after 6 cuts. Well, you just follow the pattern. So 6 cuts would obviously be 64 here, and that would be 1.25. And you could keep on going. The problem is you're going to eventually run out of area. It's going to get down to like so tiny that you can't even cut it. The number of pieces are going to get bigger and bigger and bigger as you keep going. All right. So on the given axis, sketch a graph of the number of pieces as a function of number of cuts. All right, so we're basically going to graph both columns. Okay, so I'm going to go back to my table here, and I'm gonna tell you what I'm going to do. I'm gonna copy that table. Let's do this. I'm going to screen grab this, and I'm going to send that to the next page. I should have just copied it. There we go. That way I have it here. I don't have to keep flipping back and forth. Okay, cool. So I'm going to plot that chart here. So number of cuts. So this graph here, let's see here. I'll use a highlighter here to make you see it a little bit better. So cuts and pieces. So that's kind of like I'm graphing this table here. Okay, as I drew that. Didn't mean to do that right there. There we go. All right. So I'm basically doing the left side. So 0 is at 1. 1 cut is at 2 pieces. So it's still pretty small. 2 cuts is at 4. So I'm just right below that line. 3 cuts is at 8. Starting to get a little bigger. 4 is at 16. 5's up here at 32. And we even did 6. 6 is up here, like off the chart at 64. So you can kind of see you get a graph that looks like this. I'm just going to keep going in that pattern. Okay, that's called a growth function. It starts out real small and it gets real flat and then it shoots up. Okay, now over here is, let's see here, I'll do this one here in green. That would be this column along with that column. Okay, it's like an XY table. So again, we think of this as X because it's on the X axis, if you look at that. And this is Y. Okay, same thing here. This is Y, but we have two different tables. Okay, it's two tables combined into one because we don't want to rewrite the cuts again. So 0 is at 80. 1 is at 40. 2 is at 20. 3 is at 10. 4 is at 5. 5 is at 2.5. And it goes all the way down like that. So this looks something like that. Okay, so it's decaying. It's starting at 80 and it's going down. Okay, so this function we call a growth because it's growing, which I said in the table, and this is called a decay. So let's read the rest of the question here. How can you see on the graph how the number of pieces is changing with each cut? You can just see them growing, and then in the yellow one, and then the green one, you can see it decaying. Number 4, on the given axis, sketch a graph of the area of each piece as a function of number of cuts. Oh, okay, so we did both of those already. So they're both, changing, obviously. They're not changing at a steady rate, so they aren't linear. They aren't forming a straight line. They're changing different amount every time. But you're being multiplied by the same ratio. Okay, so growth and decay. All right. All right, so let's complete each geometric sequence. So I can see right here, I'm multiplying by 2. And again, remember that trick I told you. If you want to just divide the numbers, if we're multiplying, 3 divided by 1.5 is 2. Okay. Now, a lot of times you can do the math in your head. Sometimes it'll be weird fractions and you're going to have to divide them. But times 2, times 2, times 2, times 2, times 2. Okay. So your common ratio is 2. And your first term is 1.5. Okay, we'll get to that later, but I'm just doing a little foreshadowing here. So this one, again, you could do it in your head, but remember the trick. Divide 120 divided by 40 is 3. So it's really times 3, times 3, times 3, I think is 1080. And then times 3 again is 3240. All right, this one is, remember, it's not divided by 10, it's times 1/10, okay? Times 1/10, times 1/10, times 1/10 is going to be 2 over 10, which I would reduce that to 1/5, okay? And then times 1/10, and then times 1/10, okay? So I could just do times 0.1. 0.1 is equal to 1/10. So 0.02 times 0.1, I get 0.002. Okay. D, I don't know what happened with D. D is a little messed up here on my slide. You probably have some number there. You can try that one on your own. I look at E, I'm timesing it by 1/2 again. So that's going to be 3, 1.5. Okay, so find its growth factor or growth rate. Okay, I was saying growth rate, but growth factor is the same thing. Remember, a factor is something that you multiply by, a number that you multiply by. Okay, so I did it on the first one. The second one was your growth rate. I'll just call it R. Growth factor, same thing. 3, 1/10, or 0.1. D, I'm going to skip because it didn't come out right. And this is 1/2. Your first term, A1, is 40. Your first term here is 200. And your first term, it doesn't tell us to do this, but I'm just doing it to get you used to it, is 24. All right. In your group of 2, come up with a new geometric sequence and be prepared to explain why it is a geometric sequence. Okay, I'll start out with 1 here. Let's just start out with 4. And let's do, I don't know, let's do a weird number. Let's make it different. Let's go times 1.2. So I'm just going to take my calculator. 4 times 1.2 gives me 4.8 times 1.2 is 5.76 times 1.2 is 6.912. And you could keep on going, but there you go. Let's do another one. I'm going to start out with 100. And I don't know, let's times it by 1/4. Okay, so that's going to take me down to 25 times 1/4. So I'm just going to leave it as a fraction. I'm going to make it 25 over 4 times 1/4. So that's going to be 25 over 16. And you could keep on going, okay? So you might be noticing the pattern here. When your growth rate or growth factor is greater than 1, our function or our sequence grows, okay? We call that growth. When our growth factor is between 0 and 1, that's when they keep getting smaller, and we call that decay. All right. All right, so learning goal. I understand what a geometric sequence is, and I can find missing terms in a geometric sequence. I think we're pretty good with that. Here's a cool down. Here's my sequence, 500, 120. Explain why the sequence could be geometric. We are multiplying by 1/5. Again, remember the trick I showed you, 100 divided by 500. You always divide by the previous term. Reduce it, we get 1/5. It would work with any of the numbers as long I could do 20 divided by 100. that would still give me 1/5. Okay, so what's the next term? So I would do 20 times 1/5, and that would be 4. How do I know 20 times 1/5 gives me 4? Okay. Geometric sequence, if you want to jot that down somewhere in your notebook, formal definition, a sequence in which each term is a constant times the previous term. Okay. So basically we are, you could also put a little note here, sequence that is multiplying by the same number. I don't want to just say multiplying. I want to say multiplying by the same number. That's why they say constant, because you can't multiply by 3 and then 4 and then 5. That's not a geometric sequence. You have to multiply by the same number all the way through. Okay, that's all we got here.